Hey there. Welcome back to Advanced Quantum Mechanics. This is lecture 23. So far, we have seen multiple ways to calculate quantum mechanical predictions, namely, sorry about that. Okay, so we can write f bar of t, the expectation value for some observable, always in this way. Time evolution operator, and then f hat of t naught, time evolution operator, psi. Okay, and then our first method for calculating these predictions explicitly consists in doing this. We bracket this equation in a particular way such that all the time evolution goes into the operators. So we bracket like this, and we say that this is f hat of t, and it obeys the Heisenberg equation of motion, which is that IH bar f hat dot of t is equal to commutator of f hat of t with the Heisenberg Hamiltonian. And this is the Heisenberg picture. All right, and we also showed that instead we can bracket differently, namely by having the time evolution in the states. So then we have f hat of t naught, and then u hat of t psi, and we bracket like this. And then we say that this is equal to psi of t. And this psi of t, oh, I should say, just for completeness, you know that, of course, these guys are frozen in the Heisenberg picture. Obviously, right? No time dependence here. And in the Schrodinger picture, we have that this is obeying the Schrodinger equation, IH bar d by dt, psi of t equal to Schrodinger Hamiltonian of t, psi of t. And this is the Schrodinger picture. Well, and then we found that there's yet another way of bracketing things, namely we write instead, we write that this is psi, and then u hat prime dagger and u hat easy dagger, well, of t, and then f hat of t naught and u hat easy of t, u hat prime of t, and psi, where this was a decomposition of the full unitary time evolution operator. Then, once we had decomposed things in this way, and this, of course, is u hat dagger of t, right? Once we had things written in this way, we then bracketed in the following way. We bracketed like this and like that. In this way, we have that the Dirac picture states psi of t Dirac picture, and here we have psi of t Dirac picture, and this is f hat in the Dirac picture of t. Each obey equations of motion. Namely, this one obeys an equation that looks like a Heisenberg equation. It's IH bar d by dt f hat Dirac of t is equal to commutator of f hat in the Dirac picture of t, which with the easy Hamiltonian in the Dirac picture of t. And this simply means we are solving the problem as if there was no difficult part of the Hamiltonian. And we're solving it in the Heisenberg picture. And then this guy was obeys a Schrodinger type equation, IH bar d by dt, psi of t, psi of t d equal to, and then here it's only the difficult part of the Hamiltonian, but written in the Dirac picture of t, and then psi of t in the Dirac picture, where this is a time-dependent operator in the Dirac picture, and the time-dependent operators in the Dirac picture obey that equation here, right? So the Hamiltonian as an operator, and all of the operators that are in this Hamiltonian, obey the free evolution, or obey the easy evolution according to H hat E. All right, so this is the Dirac picture here, or interaction picture. By the way, these equations are not called the Dirac equations, even though they are equations in the Dirac picture. The Dirac equation that you may have heard of is a relativistic wave equation that is independent of the Dirac picture. It has nothing, nothing to do with the Dirac picture. Now, there is something that these three pictures, the Dirac picture, the Schrodinger picture, and the Heisenberg picture have in common. And that is that none of these pictures involves calculating the time evolution operator, right? Because in the Schrodinger, in the Heisenberg picture, we bunch the time evolution operator together with the operators. And then we solve for the operators. We obtain the f hat of t. But that doesn't tell us what u hat of t is. In the case of using the Schrodinger picture, we are bunching the time evolution operators with the states. When we solve the Schrodinger equation, we get psi of t. Again, that doesn't tell us what the time evolution operator is. And here, it's a mix of the two, but at the end of the day, we calculate the f hat of t and the psi of t. Again, we don't learn what the time evolution operator is in this case. Now, there is another picture, and that is the Feynman picture. Here's also the Feynman picture. The Feynman picture goes back to square one. There we say f bar of t is, after all, psi u hat dagger of t f hat of t naught u hat of t psi, and then Feynman says freeze this and freeze this as well. Take the equation as it is, with the only time dependence in here. And then simply solve for u hat of t. In the Feynman picture, the states don't evolve in time, the operators don't evolve in time. No, they're frozen, Instead, we solve for the time evolution operator. Once we have the time evolution operator, we can then, if we want to, calculate the predictions right away using this formula. But we can also, if we want to, throw the time evolution operator onto the operators and get the solution in the Heisman picture, throw the time evolution operator onto the vectors, and we get a time evolution in the Schrodinger picture. But why would we? We can simply calculate the predictions right away if we want to. Okay, so the Feynman picture consists of calculating the time evolution operator itself directly. Now, how can we do this? How to calculate? U hat of t. Now, there are two answers to this. There is a simple answer, which we will give right away. And then there's a much deeper answer too. So, simple answer, it's relatively simple, not very simple. Simple answer is use its defining equations. And remember what they were? Well, by definition, the time evolution operator obeys these equations of motion. IH bar d by dt of u hat of t is equal to u hat of t, Heisenberg picture Hamiltonian, and the initial condition that u hat at the time t naught is equal to the identity operator. So that's the simple answer. And we will now next study exactly how to do that and how this looks like, namely by writing this down in a basis, checking out how that looks like in a basis, and then solving it. Now, why would we want to go into a basis? Well, because once we write things in a basis, especially if it's a continuous basis, we will end up with a differential equation here. And then we can use all the methods that are known for the solution, for the solving of differential equations. Whereas here on this abstract level, it's nice to see things from an overview vantage point. But for actual calculations, it's better to go into a basis so that we can then use various tools of mathematics. But there is also a deeper answer, and I will at the moment only indicate what's up, but later in the course, then we will get to it in more detail. So a deeper answer is that u hat of t can also be calculated by different methods. And this is the Feynman path integral, by the Feynman path integral. And this gives us a complete reformulation of all of quantum mechanics, yielding a complete reformulation of actually not just quantum mechanics, but all quantum theories. This is something that might not be apparent, but we will see how that comes about. For now, though, let us just do the straightforward thing and solve for the time evolution operator using its defining equation. As I said, later in the course, we will also cover the Feynman path integral. So let us just follow up on what we know so far and ask, first of all, why would we want to do this? Why would we want to calculate the time evolution operator? Isn't it enough to have the Schrodinger picture, for example, or any one of the other pictures? After all, solving for the time evolution operator is not going to be so easy. It's the u hat of t is an operator-valued function of time. And solving a differential equation whose solution is an operator-valued function of time, or in a basis a matrix-valued function of time, or a integral kernel-valued function of time, is harder than solving a differential equation for a vector-valued function of time, such as the Schrodinger equation. Right? U hat of t is an operator-valued function of time. Psi of t, Schrodinger state function of time, is just a vector-valued function of time. So why would we want to do this? Why calculate u hat of t? Now, let's compare with the effort in the Schrodinger picture, because the Schrodinger picture seems to be the simplest. And in many circumstances it is. That's why it is so popular and why first courses of quantum mechanics usually work with the Schrodinger equation. So why would we want to calculate the unitary time evolution operator instead as the central thing here? And the key answer is, well, there are many reasons, but an important answer here is this. Here, question, answer. The Schrodinger equation needs to be solved for each initial condition separately. So if we solve the Schrodinger equation for one initial condition, it doesn't help us for solving the Schrodinger equation for another initial condition. We have to start over again. This is a problem that it can be overcome by calculating u hat of t. And calculating u hat of t solves the problem for all initial conditions at once. Initial at once. How do we see this? Well, let's have a look. Let's say we solve. So assume, why? Well, assume we solve the Schrodinger equation, IH bar d by dt, psi of t equal to H Schrodinger of t, psi of t. And you have to choose what the state was at the beginning time, at t naught. Choose the psi of t naught is some initial state that we may call psi naught. Assume we solve for this. Well, then we'd have to start over again if we want to know it for another state psi naught tilde. Then for another initial condition, psi naught tilde, need to calculate again. In contrast, assume we solve the equations of motion for our time evolution operator. So we solve IH bar d by dt of u hat of t equal to h hat s of t u hat of t, with the initial condition that u hat of t naught is the identity. And you notice it's always the same initial condition. It's a differential equation, all right? Similar looking to the Schrodinger equation, but operator for an operator valued function. And the initial condition is always the same. Then, for all initial state vectors, such as psi naught or psi naught tilde, etc., we immediately obtain their time evolution. Namely, we obtain that psi of t is equal to u hat of t psi naught. And similarly, if we choose psi naught tilde as the initial condition, then we obtain that psi of t tilde is equal to u hat of t psi naught tilde. Whatever initial state we choose, we simply apply the time evolution operator on it, and we obtain the evolved Schrodinger state. Now, how do we know that? We know that we know this from the Schrodinger picture calculations, but it's also easy to check. But it's also easy to check afresh. I leave it up to you to do this. It's a nice little calculation. Right. By the way, once we have u hat of t, it doesn't mean we have to evolve the states in time. We can then also take our u hat of t that we calculated and multiply it left and right onto the operators to give them their time evolution, and then we have the Heisenberg picture solution. So once we have u hat of t, we can easily write down the Schrodinger solution, we can also, the Schrodinger picture solution, but we can also easily write down the Heisenberg picture solution. Now, as I said before, this is all nice and good when written down in this abstract way without choosing a basis. But for actual real-life problems, we need to solve actual real-life equations. And then having the tools of differential equation theory available is useful. So in practice, we do this in a basis. So in practice, calculate, oh, was the wrong letter here, calculate u hat of t in a basis. Let's make a definition now. Definition. The the operator u hat of t when written in a basis, and let's give this basis a name. Let's call it the Lambda basis, where the lambda are taken from some index set capital lambda. And the index set might be continuous, but it could also be discrete, and it could also be mixed, as usual. So the operator u hat of t, when written in a basis, i.e., we take u hat of t. Let me give it a bit more space. We take the operator, and then we look at its matrix elements in a basis. So we put here, lambda, and here we put the basis vector lambda prime. Then it is called the Green's function. In the lambda basis. Right. So this is a discrete or continuous or mixed index set. It could be like the natural numbers, but it could also be the real numbers, for example. And these matrix elements here, when we let the lambda run through the index set, capital lambda, these matrix elements are given a name. And because we want to call it a Green's function, we write it as G of lambda and lambda prime and t. Okay, so this is the definition of a Green's function in quantum mechanics, or in quantum theory. Now in practice, we often use the position eigenbasis. This is where it's coming from, but of course we can generalize this. So we can use any basis, but in practice, we often use the position basis. One often uses the position Green's function. So we then define x prime, t is equal to x u hat of t x prime. Now, what does this mean? What does the dynamics of the time evolution operator mean for the dynamics of the Green's function? So recall, what we have is that our u hat has to obey IH bar d by dt of u hat of t equal to Schrodinger picture Hamiltonian acting on u hat of t. And we have that u hat of t naught is equal to the identity operator. This means something for the matrix elements of our time evolution operator in the position basis, which is to say this operator equation of motion must translate into some equation of motion with initial conditions for the Green's function. And what is it? Well, all we need to do here is multiply this equation here from the left and from the right with a position eigenbasis. Let's do it here, for example. What do we get? We get that x u hat of t naught x prime is equal to x prime. Right? So we've just multiplied both sides of this equation from the left with x and from the right with x prime. And then what do we have? Then we have that g of x and x prime and t, because this is by definition what this is at t naught, t naught, right? Because here this is our definition of the Green's function, so we just choose t equal to t naught, is equal to delta of x minus x prime. All right, so we've already translated the initial condition into an equation for the Green's function. How about this one? Well, let's try to do it similarly. So we multiply from the left and from the right with the position eigenvectors. Then we have IH bar, we can pull this in front. We can also pull the d by dt in front. And then we have here x u hat of t x prime. Right? In principle, the IH bar d by dt is inside here, but we can pull it outside because the x is some constant position vector. And this is then equal to x, and then we have h hat s of t, u hat of t, and x prime. Now, on the left-hand side, we recognize immediately what we have here. We have IH bar d by dt of the Green's function, g of x and x prime and t, because this is literally what it is by definition, right? But on the right-hand side, we don't quite see a Green's function in this yet, but almost. Just move up the page a little bit. We're almost there. Let's just insert the resolution of the identity now, namely in here, right? At this location here, we put the resolution of the identity. Then we have equal to the integral of x, and then h hat s of t, and then x double prime, because x prime is already taken. This here is our resolution of the identity in terms of the position vectors. And then u hat of t and x prime and dx double prime, because this is the resolution of the identity here, together with the integral and integral symbol and this and that. That's the resolution of the identity, right? So we have put this in here. The identity went in here. Right, now here we recognize that this is our Green's function again. So we have, this is g of x double prime, x prime, and t. All right, so what we obtain here is an integral equation, a differential integral equation for our Green's function, right? The time derivative of the Green's function is equal to integral over the matrix elements of the Hamiltonian, multiplying the Green's function, and then that's integrated up. If we had chosen not the continuous x basis, but if we had chosen instead some discrete basis, then this would be a matrix, and that would be a matrix. Okay. Now, how does this play out in real life? Let's do this in an example. Before we move on, let's just see how that looks like in practice. So, example. I mean, ultimately, we want to simplify this, but let's first simplify it in an example, and then we'll simplify it in general. So let's say our Schrodinger Hamiltonian is p hat squared divided by 2m. Well, then, where did we arrive? Well, then we have that IH bar d by dt of g of x and x prime and t is equal to the integral over the real line of x and then Schrodinger Hamiltonian of T. Actually, we can write down the Schrodinger Hamiltonian right away. No need to do that here. So the Schrodinger Hamiltonian can be written as, let me write it like this. It's 1 over 2m, and then we have here a p hat and another p hat. It's p hat squared divided by 2m. Let me just write it like this for a moment. And then we have x double prime, right? We're over here. It just filled in what the h hat is. And then we have x double prime u hat of t, x prime dx double prime. Now, our goal has been to rewrite everything in the position basis so that we are, when we are done with it, so that we are dealing with a differential equation in the position representation. Now, for that, we need these matrix elements here. And the usual trick is that we insert here a resolution of the identity in the position basis. So what is this? You can see how this is going to get a little bit messy now. Even though we are working with the simplest quantum mechanical system there is, just a free particle, p squared over 2m. Right, but we have to go through this at least once. So what do we have? Oh, let me just write it like this. 1 over 2m. And then we have x, and then we have p hat, and then we have x triple prime, because new resolution of the identity. And then that's why we have two integrals here. And then we have another p hat here. And then x double prime, that's this one now. And then this goes on over here. We're multiplying with the x double prime, u hat of t, x prime, dx double prime, dx triple prime, where we recognize that this is, of course, a Green's function here. Okay, now, how to proceed from there? Well, let us remember that we worked out what these guys are, this one and that one. We calculated this before. And what we found is that this is equal to IH bar, and then it's d by dx double prime delta of x triple prime minus x double prime. And this one is IH bar d by dx triple prime. It's always the second one that is down here. And then delta of x minus x triple prime. So I hope you see, well, I'm sure you see already where this is going. We have here derivatives of Dirac deltas, two of them, and we have two integrals. Now, derivatives of Dirac deltas, how do we handle them? Remember, we handle them by doing the integration by parts. The boundary term will go away, and we're just left with the derivative acting on the remainder of the integrand. So if we do this, then what do we get? Well, we get that the two derivatives are thrown to the other side, which means that instead of acting on these Dirac deltas, the derivatives will act on this stuff here, on our Green's function. And the Dirac deltas will set the variables the same. They will make sure that x is equal to x triple prime, and x triple prime is equal to x double prime. So we're just left with x's. And so the derivative that used to be the derivatives that used to act on the Dirac deltas are going to act on x here in this matrix element. And the x double prime will become the x. I'm just summarizing what could also be written tediously in several lines of equation. And what we get then is that this is equal to both integrals gone, both Dirac deltas gone, the IH bar becoming a minus IH bar because of the integration by parts. This one becoming a minus IH bar because of the integration by parts. Minus IH bar times minus IH bar gives us a minus H bar squared. So we have here a minus H bar squared divided by 2m. Then as I said, the integrals will be gone, the Dirac deltas will be gone. And we have that we have a d squared by dx squared acting on this, right? Acting on x u hat of t x prime. The x double prime has become an x because there is this these two Dirac deltas. One is setting the x to x triple prime, and the other one makes the x triple prime go to x double prime. So overall, x becomes x double prime. That's why x double prime here becomes just an x. All right, so if we now summarize this, what we obtain is that, let me just show the beginning as well. We obtain that the equation of motion for the Green's function is d by dt g of x and x prime t is equal to minus h bar squared divided by 2m, and then d squared dx squared. And remember, this is the Green's function, so it's g of x and x prime and t. So what we found is that this is the position space representation of this equation here. Right? This is abstract, basis independently, and then choosing the basis, the position basis, the u hat of t becomes the g of x and x prime of t, and it obeys this equation. Now you see this is a differential equation not only in t, but a differential equation in all the variables, also in x and x prime here. So what we need to solve in the Green's function method, in the Feynman picture, is this differential equation along with the initial condition over here, right? So what we have is that this and g of x and x prime and t naught equal to delta of x minus x prime. These two represent IH bar d by dt u hat of t equal to h hat Schrodinger of t u hat of t and u hat of t naught equal to 1 in the x basis. Now, this was for the special case where the Hamiltonian was the Hamiltonian for free particle. Now, this can be written also slightly differently, because if you remember, by the shorthand notation, notice by the shorthand notation, what we have is that IH bar, well, remember the shorthand notation was that p hat dot is acting as minus IH bar d by dx, and x hat dot is acting as multiplication by x in the x basis. Right? So this was the shorthand notation for x hat and p hat's action on position in the x basis. So therefore, we can write this also as equal to p hat squared dot divided by 2m acting on g of x and x prime of t, right? Because the p hat dot is minus IH bar d by dx. P hat dot squared is minus h bar squared, second derivative. That's no accident. that's of course why we introduced the shorthand notation in the first place, namely so that these calculations, which are so predictable but so tedious, can be avoided. You see, if we had here not the second power, but the 22nd power, then we would have to introduce here 22 resolutions of the identity. We would have gotten 22 derivatives of Dirac deltas and 22 integrals. And then we would have to do 22 integrations by part. And then the end result would have been that the Dirac deltas can be canceled with the integrals. We have no more Dirac deltas, we have no more integrals. And at the end of the day, we would have to have, you know, minus IH bar to the 22nd power and 22 derivatives. And if there were also some dependencies on the position operator, remember the position operator, again, we would have to do a resolution of the identity and read an integral, but the position operator has matrix elements which are Dirac delta. So again, they cancel each other out. So the shorthand notation, if you remember, was introduced exactly to avoid having to do this all the time, so that we can jump directly to the result. Namely that when we have a Hamiltonian, which is a polynomial in the x and the p, acting on something in the position wave function, then all the p hat act by minus IH bar d by dx, and all the x hat act by multiplying by x. So in conclusion then, in the X basis, we have, we need to solve, we need to solve these two equations in order to get the time evolution operator, or in order to get the Green's function. It's the same thing, just one is abstract, one is in a basis. We need to solve IH bar d by dt g of x and x prime and t equal to, now we take the Schrodinger Hamiltonian, which is a polynomial in x hat and in p hat, and if there are multiple of them, then polynomial of multiples of those, and then x hat dot and p hat dot, and it's still of course also a function of t, acting on the Green's function g of x and x prime and t. Right? So any occurrence in here of a momentum operator will be translated. I mean, initially the Schrodinger Hamiltonian is something like p squared over 2m, but h hat of p hat squared, and then the dot is to be taken, means that the p hat is to be replaced by minus IH bar d by dx. And it gives us the same result as if we had done it carefully by writing it out, putting the position eigenvectors left and right, inserting resolutions of the identity and integration by parts, and then canceling the Dirac deltas with the integrals, right? Okay, so we have to solve this equation and g of x and x prime and t naught equal to delta of x minus x prime. So when we solve that, we're done. Then we have the Green's function, which means we actually have the time evolution operator in the position basis. Let's see how that plays out in practice. Here's an example. Let's say the Schrodinger Hamiltonian is of the form of the harmonic oscillator. Actually, it turns out there is something curious that we can see here about the harmonic oscillator that would not have been clear in either the Schrodinger picture or the Heisenberg or Dirac picture. So then we need to solve the equation IH bar d by dt g of x and x prime and t equal to, well, what is p hat dot squared? Well, it's minus h bar squared. We just calculated that. Minus h bar squared times the second derivative, so 2m, and then d squared dx squared plus m omega squared half. And we know how this thing is acting in the position basis, namely simply by multiplying by x. So we have here x squared and g of x, x prime and t. And of course also g of x and x prime and t naught at t naught is equal to delta of x minus x prime. This is what we need to solve now. And it turns out this is surprisingly hard to solve, actually, even with differential equation methods. And I will skip the derivation of this because this is not a course on differential equations. But it will give you the solution. And in fact, it's not difficult. It's a bit tedious, but it's not too difficult to check the solution. Because you just have to plug it into the differential equation here and the initial condition and verify whether it obeys that. So the solution can be shown to be g of x and x prime and t equal to, and now I have to open a big bracket here. It's quite an expression here. M omega and then 2 pi I h bar sine of omega t, all of that to the power of 1/2, and then e to the power of I m omega divided by 2 h bar sine of omega t, and then x squared plus, oh, there's another bracket here, x squared plus x prime squared times the cosine of omega t minus 2x x prime. All of that is in the exponent there. There we have it. This is the Green's function. This is the time evolution operator of the harmonic oscillator in the position basis. And you see there is quite a bit going on here. I mean, how often do we see a function that has a complex exponential which has in its denominator a sign? So obviously this is a non-trivial thing, but yeah, it contains all the information about the harmonic oscillator, everything. And in particular, we have now solved the harmonic oscillator for every initial condition at once. Because now, given an initial wave function, initial wave function, let's call it sine naught of x. Its time evolution psi of t follows immediately. You can immediately write it down. Immediately. Namely, we obtain that psi of t is equal to the integral over r of the Green's function, and forgive me if I don't write out the whole thing again, of g of x and, oh wait a moment, this thing has two variables, depends on x and depends on t, equal to g of x and x prime and t, and then psi naught of x prime dx prime. So for any wave function, doesn't have to be an eigenfunction of the harmonic oscillator or anything like that, any wave function. You can choose the wave function to be a step function, for example, or whatever function you draw by hand. doesn't matter, any psi naught you choose as the initial state vector, as the initial wave function of your harmonic oscillator. This expression, this integral here, gives you the wave function and the later time right away. You don't need to know anything about Hamid functions and things like that. No, you just integrate this against the Green's function, you get the wave function at a later point in time. Now, you may wonder, why is that called a solution? Don't we still have to do an integral to get to the psi of x and t? Isn't that non-trivial? Here I have to say that in modern physics, if you reduce your problem to the extent that all you still have to do is an integral over some known functions, like here the g and the psi naught, then you are considering yourself to be done. And that's because doing an integral, such as this one, might be tedious, but it doesn't require any ingenuity. It doesn't require any creativity. You look at the expressions and you check, can I do it analytically? And if yes, great. If not, plug it into a machine. There's no surprises can happen when you tell a machine to do this numerically. So we're basically done by the point that we are at where we only have to do an integral. Now, in this case, what I just told you here is that we can use this solution, this Green's function, to calculate how, in the Schrodinger picture, an initial wave function evolves in time, namely like this. But of course, that's not all. We are not working in the Schrodinger picture here. What we did calculate was the time evolution operator, which means we can now also calculate how, in the Heisenberg picture, any one of the operators evolves in time, simply by making use of the fact that the time evolution operator multiplied to the left and to the right of an operator at the initial time gives us the operator at later time. And if you write that down in a position basis, what you need is not the time evolution operator, what you need is the Green's function, and we have it. All right, so that's the Feynman picture. Now, there is something curious that I'd like to close this section with, which is that in the case of the harmonic oscillator, there is something special that we can read off from the Green's function here, this one. So let me make a remark. And the remark is that at time tq for t quarter period equal to pi over 2 omega, i.e. Omega tq equal to pi half, something is special. What might that be? Let us look at our harmonic oscillator Green's function. What we see is that we have cosines of omega t and we have sines of omega t. Now, when omega t is running from 0 to 2 pi, then we have a full oscillation of the harmonic oscillator, right? When omega t is running from 0 to 2 pi, then the cosine runs all the way from 0 to +1 to 0 to -1 to 0 again, and we have completed a full oscillation. Now, when omega t is not 2 pi, but when omega t reaches pi half, well, then we have a quarter period. Right? Not even half a period, we have just a quarter period then. And what happens when omega t is pi half? When omega t is pi half, which is to say at a quarter period, omega tq is pi half, which is to say tq is pi over 2 omega. What then happens is that the cosine which started out at 0, which started out at 1, cosine of 0 is 1, and the cosine after a quarter period becomes 0. So that term disappears up here in the exponent. The sine term here becomes a 1, and that sine term here becomes a 1, the quarter period. But importantly, and that's what I want to point out here, this term vanishes at TQ. Now, why does that matter? Well, you see, what that means is that the Green's function has structurally the form of a Fourier factor. You see, this at the quarter period, this is just some number, right? Here's m omega 2 pi I h bar, and then you have 1, because the sine of omega tq is 1, and the square root of that. Just some prefactor, doesn't matter exactly what the value of it is. Here too, just some prefactor, almost the same as this one here, right? So just some prefactor, some numerical value with an I in front. This thing is gone, let's not think about it, it's just gone. And instead we just have here xx prime. So what we see here is that the Green's function becomes number, a constant number, times e to the power of I times a constant times xx prime. So what we have is that then g of xx prime and t q is equal to some constant times e to the power of I times some other constant, c2, and then x prime. Oh, did I write x1, x2? No, xx prime, fine, xx prime, right. So this means that psi of x and tq, so after the wave function, after a quarter period of the harmonic oscillator, is equal to the integral over r, and then it is c1 e to the power I c2. In the lecture notes I'm writing out, spelling out what c1 and c2 are, of course it's trivial. And then we have x prime, and then we have psi naught, the initial condition wave function of x prime dx prime. And you notice this is a Fourier transform. So what we see here is that apart from these constants, C1 and C2, which we can make, we can give them any numerical value we want just by choosing the units the way we want. We obtain that this is the Fourier transform of psi naught of x prime. Now that's curious, because ordinarily the Fourier transform is an operation that we need to do in the computer. But here, nature does it for us. When you have a harmonic oscillator and it is prepared in whatever state we want, then after a quarter period, the wave function becomes its Fourier transform. And a quarter period later, it is again Fourier transform. A quarter period later, it's again Fourier transform. So the harmonic oscillator is a Fourier transform machine. Now, why would we care about Fourier transforms? Now, Fourier transforms are, of course, super important in signal processing, and of course in physics all over the place too. but also in signal processing and in quantum computing. The most famous algorithm that has so far been proposed for quantum computers is Shor's algorithm for the factoring of integers. You know, the kind of thing that is capable of breaking codes. And it has as its central part a quantum Fourier transform. Now that quantum Fourier transform is not done using a quantum harmonic oscillator, but maybe there's a way to use the quantum harmonic oscillator for it. At the moment, we do the quantum Fourier transforms in a more pedestrian way in quantum computers. In any case, I find it cool to keep that in mind, that the harmonic oscillator can be viewed as a Fourier transform machine. All right, so now we have completed the Heisenberg picture, the Schrodinger picture, the Dirac picture, and now the Feynman picture. I gave you only the basics of the Feynman picture so far. We calculated the Feynman propagator the conventional way here. I just wrote down the differential equations that it has to obey, and then we just used the differential equations method to solve that. But as I indicated at the beginning of this lecture today, there are completely different methods for calculating the Green's function. And since once you have the Green's function, you have the time evolution operator, you have solved the quantum mechanical problem, we can say that a new method for calculating the Green's function is a new method for doing quantum mechanics. And Feynman discovered such a method, inspired by some comments of Dirac. Feynman found a method that is completely different from anything that we've seen before, namely the so-called path integral, with which one can calculate Green's functions. We will get to that later on. We will do it only later because there's much more to be done within the framework that we have developed so far. Okay, this is as far as we get today. See you then. Bye-bye.